Okay, so let's try to understand SVM overview and its applications. SVM is a supervised machine learning algorithm which can be used for classification and regression problems. The simple idea that SVM works is to differentiate the two classes of data using a line, which we call it as a hyperplane. Hyperplane works in this way. So it finds an optimal line between the two classes, but at the same time, it also maintains the maximum distances between the two classes. Okay, so we will get into the concept of hyperplane in the coming slides. Before we jump onto that, we will try to understand the SVM applications as well. So SVM is used in text classification tasks such as category assignments, spam detections, sentiment analysis, and commonly used in image recognition challenges, color-based classifications, and it plays a very vital role in areas of handwritten digital documents. So the goal of SVM is to identify an optimal separating hyperplane which maximizes the margin between the classes of a training data. Okay, so let's try to understand in 2D space. As you can see the figure, the same picture that we are trying to take from a data set of an email data, wherein we are trying to find a spam or ham. And if we take that data and then try to plot it, and then you see that both sides, two different classes and separated by a hyperplane. However, there are many different ways that you can actually draw the line to differentiate. On what situations that we decide that this is the best one. Okay, so as we discussed just now, finding an optimal hyperplane is one thing just to differentiate, but you also need to maintain the maximum margin between the two different data sets. So you have to take the distance between the closest point of differentiation from both sides, and then you have to have a parallel boundary lines to that, and then have to decide the maximum margin in a 2D hyperplane. We will see how we can able to handle this thing in 2D, 3D, and then in this different space. Okay, so we will move on to understand more about the margins now. See, thus a good classifier it must choose one of the infinite number of the hyperplanes. As we have just now seen, there are many different lines that you can draw, but a classifier should be able to help us identify the best optimal line. Okay, so that it not only performs just only with the training data set, but it also have to perform that in the test data set. So if you see that picture right now, the positives are on the one side, the negatives are on the one side. Well, in an ideal scenario, it may not be in such way, but just for the sake of understanding the concept, we have taken this example. So the positives and negatives are both sides differentiated by the line H1, and H1 is nothing but the hyperplane, and then there are two dotted red dots, that's B22 and B12. So these two, sorry, B11 and B12, which are actually the boundary lines of the, which are actually parallel, and then the boundary lines of the hyperplane. So it actually trying to find the maximum space between these two. How much is the distance that you can go to the positive side till it touches the point nearest to that, and then it creates a boundary line, and then to the right side of it also it does the same thing. So that's how the boundary line has been drawn to find an optimal line. Well, you can also say there is one more line that actually comes in a green line, which also says that there is one more hyperline with the decision boundaries as well, with B21 and B22 also can be drawn. But you can closely observe the distance of H1, the width of M1, the red one versus the green one is less. Okay, so the M1 is higher in terms of margin versus the behind one. Okay, so to get the best one in this particular situation is the N1. So you have to take the best hyperplane with the maximum boundaries, maximum width. So you take a H1 as the hyperplane of this situation. So that's how the margins helps us. And the points that are on the boundary lines are named as support vectors. So those are actually the points which are helping us to decide where you can have a boundary line in parallel to your desired hyperplane. Okay, so moving ahead, we will try to understand about the linear SVM. As we have seen, if there is a data, wherever it is possible to classify them, or wherever we can able to linearly separable them, is called a linear SVM. So in other words, that it actually, in a linear SVM, it searches for the maximum margin hyperplane. Okay, so if we have to put that in a mathematical form, I'm sure you might have covered this concept of logistic regression and linear regression in the past, and then you might have gone through the expression of a line to understand the slope and then the intercept. Y is equal to mx plus b, mx plus c, where m is the intercept and then c is being the slope. So we take the same expression of line here also, and then we depict that with w dot x plus b is equal to 0, where w is actually the vector from w1 to wn, and x1 and x2 are all the values in the data set, and b is a real constant. Okay, so we take these points and then we try to put that in the formula, and we try to decide that if anything, any point which is actually on the hyperplane, we name it as the value 0, and any points which are, when points in the sense any values which actually falls towards the one side of the boundary, negative side can be termed as less than 0, and the other side, which is actually the positive side of it, is greater than 0. So if you put that in expression forms, in the example that we have depicted here, consider any 2 points x plus and x minus. If you have to put that in an equation, the equation of an x plus located above the decision boundary is w dot x plus b is equal to k. K is the value that we are actually trying to figure it out, the value of what actually it figures out. So any value that you are trying to figure it out using this expression, if the w of x falls on other side greater than, so positive side of it should be greater than 0, and similarly any point which is located below the decision boundary line it will be treated as k is equal to less than 0. So if you take a training data set, and then if you are trying to find all the values of class label y of any data set, and then if you are trying to put that in an expression, so it's like y is the value of the label will be positive if w dot x plus b is greater than 0, and it will be negative if w dot x is less than 0. See, so far we are trying to understand the concept of SVM, and then we are trying to put that in a formulation, mathematical formulation, by taking the linear expression. But so far we have not actually calculated the margin using this equation. So we will get into those formation of the logic. So you see this one, at the top of this picture, you see that there is a clear hyperplane with the 2 different boundary lines. Wx plus b is equal to 0, which is the center line, which is hyperplane, and is equal to 1, which is on the other side of the boundary line with the class plus 1. This side, which is on the negative side, will be as minus 1. So we know that w dot x positive side plus the b, which is a constant, is equal to plus 1, and negative side will be treated as minus 1. So if you are trying to, you can also able to write in the same way that w dot x plus minus x minus is equal to 2, because 1 and then minus of minus 1 is actually 2, so it's 2, which is actually nothing but the distance from the positive and to the negative side, the maximum distance that we test to. So what happens is that now, what is actually the margin now? So margin is equal to 2 by the magnitude. W is what's actually the vector does have a magnitude, so 2 by the W is the formula. So by substituting the values that you get it in the data set into this particular formula will actually help us give the margin of the hyperplanes in a linear SVM. So in a real sense, you actually don't need to do all those kind of things, and then the scikit-learn, the algorithm will automatically take care of that. provided you need to understand the core basics of this particular things, what's happening at the back. Okay, so that's how the linear SVM works. Okay,